Can you hear me? Okay. Okay. First of all, I would like to thank organizers for inviting me here, and also for flexibly rearrangement in my slot for handling the Japanese the typhoon accident. So this is the presentation of the title of my presentation on replica-BP correspondence in rotational invariant spinous models. Okay, so this is outline. So let's start with the background. Okay, this is very famous model, Sherrington-Kirkpatrick model, right? And this is the first model that we could perform the replica analysis in some exactly. So that it is very famous equation, replica symmetric solution is obtained by solving. So okay, this third point equations. But if the solution satisfies this condition, it is known that the replica symmetry solution is invalid. So we have to further perform the replica symmetry breaking. Okay, this is very the famous work. And 16 years ago, for the same model, I applied belief propagation algorithm, which is known as the approximate inference algorithm, developed in the artificial intelligence research. And the result is this one. And after this, Bolshausen showed this is the mathematically rigorous way. And you can see that this is the algorithm, so you have the time index here. But at the fixed point, this is reduced to the well-known Thouless-Anderson-Palmer equation for the SK model. And I also performed how this dynamics is macroscopically characterized and derived this macroscopic equation. So this is currently known as the state evolution, right? This one. And also, I examined that when the fixed point of this algorithm is stable under this BP dynamics, and we had this equation here, this condition here, right? So I want to emphasize that these results are consequences of the dynamical analysis of the belief propagation, the current work, the AMP, right? So this is a comparison of the two analyses. Okay, this is the this is the case of the RS phase, and this is RSP phase. Okay, under this condition, the markers shows the results, experimental results of the BP equation, the update, and the curves represent the consequence of the state evolution, right? So you can see these two accord excellently. And also on the RSP phase, also these two are in very good accordance. But you can see that here inset, this plots the difference between the state vectors between the two successive times. In the RS phase, this decayed to 0. So this means that the algorithm combines the fixed point. But in the other RSP phase, it keeps finite value. This means that macroscopically, the dynamics converge to some state, but microscopically, it keep moving. Right? So the fixed point is unstable. So okay, we have two formalism. First one, the replica method. This is for the statistic analysis, and belief propagation is some kind of dynamical analysis. But you can see that comparing the two, very similar. Okay, in the case of the AMP. Right. The macroscopic dynamics is described by just iterative substitution of the replica symmetric third point equation. And the T instability derived by the static analysis by the replica method and the instability of the AMP fixed point, these two conditions are completely the same. Okay? And this is not only for the SK model. The same similar correspondence also holds for the CDMA and Hoppeed model and complex sensing models. Okay. This is background. Hi.
The two lower expressions are the same.
No, this has a time index here.
No, the lower.
Lower.
Instability equations are the same.
Same. We have to insert a fixed point. Right? So you can see that we have a space here. Right. The instability constant for the fixed point. Right?
Are the same.
Same. Same. Yes.
No, the problem seems that the formula would be equal.
Yeah. The formula is the same. Okay? So the motivation. Okay? Now, other than the SK model, we have generalized one. So rotationally invariant model. This is first introduced by Parisian Potters in 1994, right? And later, many people are playing this model. So this is formally it seems very similar to the SK model, right? But the difference is that the statistics for Jij is different. Okay, SK model case, Jij is sampled from an IID distribution, right? But in this case, Jij characterized by this expression. So the first we decompose it eigenvalue decomposition, and we assume that the eigenvalues lambda I follow the some fixed distribution, and O the eigenbases are assumed to sample from the uniform distribution or from orthogonal matrices. Okay, so this means that components connection matrices can be weakly correlated, instead different from the SK model. But still, exact analysis is possible by the replica method using some characteristic function for the matrix ensemble. This characterizes this ensemble. Okay, this is statistical analysis. And also, we can perform BP-like analysis. Okay, by using a technique of expectation propagation, which is recently, originally proposed by Minka, 2001, and was recently rediscovered as a vector approximate message passing bump. Okay, then it would be a natural question that how is the replica-BP correspondence generalized? Okay, this is motivation. So the purpose of my talk is to investigate how macroscopic dynamics or the state of evolution of expectation propagation is related to the replica symmetry solution and its stability in the rotationally invariant spin-glass models. Okay? Okay. Then next, let's turn to the review of the replica analysis of the rotationally invariant spin-glass models. Okay, this is the definition of partition function, right? And again, this is a definition of the rotationally invariant matrix ensemble. Okay, so this is a standard replica analysis. First, we compute the moments of the partition function for the natural number n. Then we have an expression of this form. Okay, and the key point is that the Boltzmann weights, the moments of Boltzmann weights for the rotational invariance assumption, the models can be expressed by using the characteristic function of this ensemble. Okay? When the replica spins are in the replica symmetry configurations characterized by these conditions. Okay? And here, the G function, this characteristic function is defined by these expressions. Okay? First, it's defined by the average over the matrix ensembles, but this practically reduced to the average over the spherical integration of the spherical spins. And finally, we get this kind of expression using the eigenvalue distribution, right? Then using the G function, we can get the expression of the RS free entropy, like this form. And we can get formally the replica symmetric saddle point equation here. And also we get the expression of the AT instability condition here. Okay? So if we insert G for the G, the function of x squared over 4, then we can reduce the result of the SK model, right? Okay, then next, let's see what we can get for the expectation propagation for this model. So this is a method of the approximate inference proposed by the Minka, right? Roughly speaking, this is a combination of the belief propagation and the approximation by the exponential family, but mostly by Gaussians, right? And we can yield the accurate inference even when the couplings are statistically correlated. This is the point. Okay, again, let's write down this is the Boltzmann distribution here, right, for the Ising model. And normally, for deriving the approximate message passing or the belief propagation, we graphically express this distribution by the bipartite graph, like this. But we can also express this distribution by this form, by handling the variable, the correction of the variables one node, and the correction of the factors by one square node, right? So, these nodes represent vectors. So some people recently call this algorithm the vector AMP. Right. And but actually, exactly computing the Boltzmann distribution is very difficult, computationally difficult. This is caused by the couplings here, because it has a coupling of the quadratic form interactions, and also this discreteness. Since it is Ising spins, we cannot apply the integration, right? Okay, but this can be resolved by the introducing Gaussian approximation, right? So here we represent this one. This square is a Gaussian form, so interaction part, and we represent by this node by the Ising term, right? These are okay. So only this we can compute analytically, but because this is Gaussian, right? So quadratic form, and also if only this form, we can also compute averages because this is factorized. Okay, but combining these two makes the computation difficult. So we approximate it by the introducing the factorized Gaussians. So here. Right. Okay, second line, we replace the blue part by the factorized Gaussian. But also we can do that, the similar thing by replacing the red part by another factorized Gaussian. And by combining the two, we can also, the third expression that can be, one can handle the computation. And here, in this expression, we assume that the prefactors, the quadratic part, or the constant, not dependent on the sites. So assuming that self-averaging property. Okay? Then we have three types of expressions which are feasible, right? Then for each expressions, we can get the expression of the moments. First moment, if we use the left expression, the first moment is given by this form, and second moment can be expressed by this form. And the middle expression, we have this. And the second moment, this. And the right expressions, we have this form. This is Gaussians. Okay? But here, since we are dealing with Gaussians, the second moment of macroscopic second moment is a constant. So we introduce this condition by the spherical constraint, like this, in the second moment. And after the approximation, these three expressions should be consistent. So we required moment matching conditions. Okay, so these three should be the equal. So for this, we introduce the expectation propagation algorithm, right? So this is summarized as follows. First, this is the initialization for the lambda f and the gamma f. This is parameters for the factorized Gaussian, set to 0. And repeat the 1 to 4 until convergence. The first, we compute expectations using right expression, like this, by the Ising expression. And after computing this, we propagate the message to the left node here, right. Then we compute again the expectations so that the spherical constraints are satisfied in the second moment. Okay? And after computing this, we propagate again to the right nodes here. Okay. Just a repetition of these procedures. And after convergence, the output is the M itself. This is the magnetization of this system. Okay, remark. Okay. Actually, the fixed point equation goes with the adaptive tap constant diagonal approximated adaptive tap equation proposed by the Opper and Winder, right? And this is a fixed point condition. And this part corresponds to the Onsaga direction term. And in the case of the SK model, we can show that this Onsaga term accords to the J square beta 1 minus Q, and it is known for the SK model. Okay. The known result is retrieved. Remark 2 is that macroscopic dynamics of the expectation propagation. Okay. Then we suppose for deriving this, we suppose that the parameters of the first, the linear term. Okay, the parameters of linear term is distributed by Gaussians and characterized by its variance Q hat. Right? And also in the Gaussian part, we assume that this is a Gaussian and characterized by the variance Q hat G. Then we can derive this type of this equation. First, we compute the Ising part Q, and using this, we have Q hat Z, right? And having this to satisfy the spherical constraint, we find the Lagrange multiplier lambda G and propagate, and compute the Q for the Gaussian part, and compute Q hat F, and just repeat until convergence. And actually, this looks slightly complicated, but the fixed point is shared with the corresponding replica symmetry saddle point equations. And so this is consistent with the replica symmetry solution. But different from the AMP, the dynamics is not identical to its iterative substitution. This is the replica symmetry saddle point equation. Right. And the remark 3 is that stability of the fixed point of the expectation propagation. For examining this, we assume that parameters are at the fixed point and just at the perturbation, small perturbation. This is characterized by the delta Q hat F and delta Q hat G, right? And assume that these fluctuations are Gaussian, right? And by this small perturbation, there's no inference for the macroscopic quantities such as the Edwards-Anderson the parameters Q. Then we can perform the linear stability analysis for the linear terms per parameters and for the right hand side and the left hand side. Okay. Then we can derive evolution, the mapping of the Q hat G and delta Q hat G and delta Q hat F. Okay. It's related linearly with each other. Then we can get instability condition of the fixed point by computing the growth rate of the variance. So if the growth rate is greater than 1, it indicates the unstable, right? Instability. But after rearranging this condition, we can get this form, this form, okay? And actually, this is nothing but this can be expressed by using the characteristic function like this. And actually, this condition is nothing but AT instability condition for the rotational invariance models. Okay. So to validate the result, I did some experiment for the SK model. Okay. This condition, okay, first one is the RS stable case. J equals 1.6 and H equals 0.8. It is known that the AT stability is satisfied. The green curves represent macroscopic dynamics of the AMP, and it is just the iterative substitution of the RS saddle point equation. And blue one, QAMP. Okay, blue curves are macroscopic dynamics, and green markers is the result of the AMP, right? So we can retrieve the known replica-BP correspondence here, and orange curve and red markers are for the expectation propagation. Okay, we can see that these two are the trajectory of these two are different, but finally converge to the same fixed point, right? This is Q and M, and the third panel shows that difference of the state vectors between the two successive times. You can see that this RS stable condition, it converges for actually the exponentially, right? The second experiment for the RS, the AT unstable case, the replica symmetry is broken. Okay, again, macroscopically, actually the result of a numerical simulation and macroscopic dynamics occurs very well. But you can see that this is the RSB case, so the difference of the state between the two successive times does not converge to 0, kept finite. So this characterized replica symmetry breaking by the expectation propagation, right? So discussion. So my first motivation was that for SKG model, the macroscopic dynamics of the NP is described by the just naive iterative substitution of the replica symmetric starting point equation. But in general, in the EP case, this correspondence does not hold, right? But the instability condition, okay? Actually, in the case of also in the case of the EP, the rotational invariance case, it seems that the AT instability condition and the fixed point, the instability of the fixed point EP dynamics are formally actually formally accord. And expectation propagation exhibits faster convergence than AMP in terms of iterations for the SK model. And this also was the case for the Hopfield model and CDMA and complex sensing models. But this is natural because expectation propagation uses matrix inversion in the dynamics. As naive application which requires more computation per iteration than AMP. So we pay a lot of cost. So that we can enjoy the faster convergence. But as long as the self-averaging treatment, so the macroscopic second moment matching is employed, the inversion operation is necessary only once at the beginning. Okay? Then the computational cost in the main loop is identical to that of AMP. So, conclusion. We here examine the expectation propagation in the rotationally invariant spin-glass models. And the conclusion is that replica symmetric saddle point equation and state evolution correspondence does not hold in general. But the instability and dynamical instability correspondence generally holds. And comments. Okay. After I calculated this one, I realized that results similar to those of this talk were obtained in a recent paper based on the free probability theory, right? The Checkmark and Oppa recent paper. So the contribution of this talk probably the naive derivation of the results based on the physical intuition. Okay. So thank you for your listening.
Are there questions?
Can I ask about the failure of the Boltzmann iteration scheme to converge below the 80 line?
Mm-hmm.
Would you deduce from that the Milano solution?
Okay, the failure, the instability of the this okay condition, right? Maybe this figure, okay, this panel, okay. So the failure is that, okay, so macroscopically, actually the dynamics looks to converge some point. But the point is that this does not converge to some point. So just continue to move.
So chaotic.
Chaotic. In some sense, yes. Yeah.
They are fixed points, but you don't find them This is for random initial conditions.
Yeah.
Another question? Then let's thank the speaker and proceed upstairs to coffee.